Welcome back to CHM421, which is analytical chemistry. We are still in topic 4 on the trigonometric analysis. So we continue our learning on acid-base titration. The last video we did some example calculation related to back titration. So in this video also, we will continue a few examples. We do it together. All right. So again, we try to solve whatever question. So we have to very careful or read carefully that question. Take note all the information given. So in this question or in this example is a back titration. So what is the question all about? 0.1504 gram of impure sample containing magnesium carbonate, because magnesium is 2 plus, carbonate minus, so the formula is magnesium carbonate. Dissolve in 500 ml of 0.01 molar of hydrochloric acid. Then we'll to eliminate CO2. So this HCl with 50 ml and 0.11 for 0 molar. The amount of impure sample. So this one impure sample, this one is magnesium carbonate. So impure sample is 0.144 gram. Then to eliminate CO2. So here is using back titration of excess acid required 21 ml of 0.0982 molar sodium hydroxide. So this HCl is excess. So the second titration is using sodium hydroxide with 21 ml 0.0984 molar. So determine the percentage of magnesium carbonate in the sample. Percentage of magnesium carbonate in the sample. So meaning that you have to know how many grams of magnesium carbonate in 0.104 gram sample, because in order to calculate the percentage, so you will use the formula x gram over 0.104 gram times 100. So now you have to do the calculation to calculate what is the mass of magnesium calcium carbonate. Okay, so uh, similar like the previous example, the first titration is HCl in excess, and then analyze with magnesium carbonate. So second titration, uh, HCl excess titrated with sodium hydroxide. This one. So this is a strong acid. This one is a strong base. So it's the same thing that we did before. We have because the chemical equation is not given, so we have to come up with the chemical equation first. So the first chemical equation is between magnesium carbonate plus hydrochloric acid to produce magnesium chloride plus H2O and also CO2. And here is already mentioned to remove the CO2. So balance the equation, magnesium, okay, so chlorine should be 2 because chlorine is CO2. So double check magnesium, okay, okay, CO3, CO2, 1, CO3, 2 hydrogen, or Cl, 2Cl. Okay, this one is correct. So the second equation is between HCl and sodium hydroxide. So we're going to get sodium chloride plus H2. Is it balanced? Sodium, chloride, H2O. Okay, it's balanced. So remember to label this one hydrochloric is excess amount. That's why we need back calculation. So the first thing you should do is you have to calculate the uh, mole number of hydrochloric acid. So you are given this information. So you can use the formula of molarity, this mole per liter. All right. So 0.11 uh, 0.1140 mole times volume. So volume is 50 ml. So 50 divided by 1000. So supposedly you can give the answer. We double check 0.1140. So 0.00.7. Okay. So this one correct. All right. So back titration is between hydrochloric acid with sodium hydroxide. So uh, sodium hydroxide, the amounts, the molarity in volume are already given. So you can calculate the mole of sodium hydroxide first. Okay. So the 0.0981 mole per liter times 2421. So 2421 divided by 1000 times 0.0902. So you can get 2.373 millimole. Okay, so this one is still what is here? It's the same thing. Okay. All right. So you already know the amount, the mole of sodium hydroxide. So what is the relationship in big titration? 1 mole of hydrochloric reacted with 1 mole of sodium hydroxide. So you pin it on the statement before mole HCl equivalent to 2.373 times mole. Okay, so the amount of HCl reacted with carbonate. So you have to, this one is gas. So you have to get the right amount of HCl reacted. The excess, the mole in excess minus with the mole from the back titration. So 5.7 minus 2.373. So you can get 5.7 minus 2.373. 3.327 to the power minus 3. So you, this one also correct. Okay. So now you have the relationship between magnesium carbonate with sodium chloride. So 1 mole of magnesium carbonate will react with 2 mole of hydrochloric acid. So this is the formula that we do here. So we know 2 mole of you know 2 mole HCl reacted with 1 mole NH3CO3. So you already calculate the number of mole for hydrochloric acid, and here 3.327. So 3.327 mole HCl. You want to know what is the mole of magnesium carbonate. So you just cross multiplication. So 3.327 times 1 divided by 2. So 3.327 power of minus 3 times 1 divided 2. 1.6635 10 to the power of minus 3. So This is correct. So you already know the mole, so you can calculate the mass because you know uh, mole is mass over mole mass. So in order to calculate the mass, this mole have to multiply by molar mass. So mass of magnesium carbonate in sample, this mole number times molar mass of magnesium carbonate. So this molar mass of magnesium carbonate, you can refer the periodic table. So times 84.33. So 0.1443. So now it's asking you what? It's asking you what is the percentage of magnesium carbonate. So you will just, as I mentioned just now, at the beginning of the question, you have to over by mass of sample. So the mass of magnesium carbonate that you obtain from your calculation divided the mass of sample and then times 100. So you can get 0.1403 over 0.1504 times 100. So you obtain 93.28%. Okay. All right. So we're done for this question. We move to another question. As usual, we read the question carefully in order to understand. The concentration of ethyl acetate in a sample was determined by diluting 10 ml of sample to 100 milliliter. So meaning that I can write this here. This sample containing what? CH3, COO, C2, H5, ethyl acetate, and then take 10 ml of sample, diluted in diluted ml, diluted in 100 ml. Okay. Volume of 20 ml, and then from the 100 ml of the diluted solution, and then from here, check it out, 20 ml of this diluted solution will be refluxed with 45 ml 0.0250 molar KOH. So this 20 ml of sample will be reacted with KOH with 45 ml, and from 45 ml with what? 45 ml with 0.0254 molar. The reaction is followed. So reaction is given between the acetic with hydroxide. This one is hydroxide. This is from, oh sorry, this one is from KOH. Okay. After cooling the excess, meaning that, oh, okay, this one is it gets in excess amount. So this one is after cooling, the excess hydroxide was back separated with 3.5 ml of 0.05 molar H2SO4. So second equation using H2SO4 with what? 3.5 ml 0.05 of molar. So the excess amount or H minus or ialah OH minus or OH. Okay, this one in excess. Calculate the weight of acetate. Calculate the weight of acetate per 100 ml. Weight of acetate per 100 ml in the initial sample. So in here. So it wants to know what is the how many grams of CH3COO Q2 H5 in 100 ml of sample. So the mass of this X gram in 100 ml, it will be similar with the mass and then the X gram of in 10 ml. Okay, this is similar. So the only difference is in terms of concentration, because this one is diluted, so the concentration should be lower. But in terms of mass, should be similar. So, alright. So we have to know the mass of ethyl acetate. So we should know what is the mole of acetate. In order to know the mole of acetate, we should know the mole of this one. But this is in excess one, so the mole of excess should be treated with this one. So we have to calculate the mole of this one to correlate with this mole, so you can get this mole, and then the mole of excess, and then we minus from the mole. You can calculate the mole of this one, and then the mole of this one, and then you can calculate the mass of this one. Yeah, I think it's a same question like before, so you can try by your own. I didn't want to further explain about it. It's a very similar. First, write the chemical equation, the balanced chemical equation. It's already given, it's here. And then the second back declaration chemical equation is between KOH with H2SO4. And then you have to calculate the mass of mole of acetic acid excess This one is the mole of KOH space. So I won't show it. So you just do it by yourself, and then you have to calculate the mole of H2. So 4, and then after you calculate the mole, you obtain the mole, you see what is the relationship between KOH with the mole. 2 KOH, 2 mole of KOH will react with 1 mole of H2SO4. So you can obtain the mole of KOH excess, and then you have to minus the mole of KOH in excess with the mole of KOH in saturation, and then you can obtain the mole number. So this one you have to try by your own because we did the example already. This is a similar approach, so you have to try by your own. And then after you obtain the mole number of KOH, so this is um, the mole of KOH. Maybe like that with CH3COOO CH1. So by using chemical equation, you can calculate the mole of CH3COO C2H1. So from here is a 1-to-1. So the mole of ethyl acetate is 7.75 to the power 10 to the power minus 4. Okay, and then yeah, you already obtained this one. So from the mole, because it's a diluted, this is a mole number in here, 20 ml. So the concentration of 20 ml with concentration of 100 ml is same concentration because it's no dilution. Alright. So you can calculate the molarity. What do we need to calculate the molarity? Okay, hold on. We have a mole, and then we can calculate the molarity is mole per liter. Let's say in 20 ml. Molarity is 7.75 10 to the power 4 mole over, and 20, as I mentioned just now, the 20 ml is similar to 100 ml in terms of concentration. Yes, because in 20 ml is not for the what? It's not for the dilution. So it's no further dilution. So in 20 ml, similar to 100 ml. So we can use 100 ml if you want. Okay. So 100 ml, 100 ml over 1000. 100 ml over 1000. So 100 ml over 1000 is 0.001. So 7.75 minus 4, 0.0075 molarity. 20. As I mentioned just now, uh, volume of 20 ml is diluted. So this concentration is new concentration. So this concentration becomes this concentration is same to this concentration. Same. This is 20. So let's say I do it this way. I try another way. So 7.7 5 power minus 4 divided 0.1. 0.0 0.0 0.775. Let's say molar mole. So I use another way and just try. And we want to know the molarity in diluted and molarity in powder. Okay, let's say X this time and 1 plus 1 quarter. And into and, 100. And then 1 will be 0.00705 times 100 divided by 10. 5 mole. And then what are we doing? Molarity is on milliliter. So something wrong. Okay, hold on. Just double check. We already know the mole. We know the mole of acetic. We know the mole of acetic. So now we already know the mole of other things. Example, acetic, and then we take 10 ml, and then we prepare the working solution of 100 ml, and then we take out 20 ml for preparation. So the 20 ml used for calculation. So the mole number that we obtain is the mole of in 20 ml. So in 20 ml is 7.75 power minus 4 mole CH3 COO to H5. Okay, so I think we can delete this first because it's something wrong. So from the molarity, because from here you can know molarity is a mole per liter, 7.75 liter, 0.20 ml divided by 1000, 0.02. So 7.75 minus 4 divided 0.02. So 0.0 0.387 5 7 5 mole. Okay. So this one is 20 ml. Okay. So change this here. So the concentration of 20 ml, it should similar with the concentration of this because it's a concentrated solution. Let's say this one is Y molarity. So when you figure out another 20 ml, it's also carry Y m because it's not diluted. But this Ym is not similar with X molar with P because this one is diluted. So what you can do is you can calculate the mole in here. In terms of concentration, it's the same. So this one is in 20 ml. So molarity in 100 ml also 0.03875 molar. So if you want to use mole is very related with the volume. So we know the molarity, we know the volume, we want to know the number of mole. Okay, so the number of mole is molarity times liter. So in 100 ml, 0.08 molar times 100 over 1000. 0.1 times 0.0388 or 875. So 0.08 is 1. Okay. So the mole number, mole A will be similar with mole Hg at the beginning because you this H mole it on and then you dissolve. So the mole for the mass mole multiplied by molecular mass, you can calculate from the periodic table. So times 81. Okay, so you can obtain this one. Alright. So what is the question? What is the weight of acetic acid? Okay, yeah, this is the answer. Okay. All right. Okay. Let's try another example. See is it similar or not like before. K2CO3 solution was prepared by dissolving 0.65 gram K2CO4 in sufficient water to produce 250 ml of solution. So meaning that we have this solution K2CO3. So we dissolve 0.65 gram and then we mark up to make it 450 ml. Okay, so that's the first step. Okay, the second statement, 20 ml of the allopate is taken. So from 250, uh, 20 ml is taken and put it in aluminum flask. 20 ml is that 0.1 molar HCl is needed into the flask. The resulting solution is then titrated with it's a double titration. So this one, the 20 ml of K2CO3 titrated with first titration using so hydrochloric acid 20 ml 0.17 molar HCl. Okay, the resulting solution is then titrated. So meaning that this K2C43 20 ml and then titrated again with another 0.12. Oh, it's not in X. This one is wrong. Okay. The excess amount should be fine. So the titrate with 0.12 molar of sodium hydroxide. So second titration using sodium hydroxide with 0.12 molar. And then you know this excess amount is HCl with 20 ml 0.4 molar. Okay, so calculate the volume of sodium hydroxide required for the bed temperature. It's asking you what is the volume of this one. So I think it's the same like before. In this case, it's slightly different. The HCl, the analyte in the aluminum flask, we know the volume and also the molarity. So we can calculate the ml of the number. Okay. So this one is in the axis one. So we should calculate what is the, this is the axis one. So you have to calculate the molarity of HCl reacted. Okay, so uh, yeah, molarity of HCl reacted. So initial mole of HCl, so this is the equation involved. First, K2CO3 will to HCl, and then the excess of HCl will be titrated by fixed titration using sodium hydroxide. So this one is this. So P and L 0.17 log K2CO3. We know that K2CO3 is a 0.65 gram in K2CO3. So this one we know 0.65 gram, and then we can get a mole number. We can calculate the mole, and then we prepare the solution of 250 ml. So we can obtain mole per liter. So from this mole per liter, you figure out 20 ml with X along 50. So this one we say X along 50. So this X molarity reacted with this one. So by using N1, G1, N2, G2, you can know what is molarity and 20 ml. So from the molarity of 20 ml, you can calculate the mole of 20 ml. So this being a mole K2CO3 in 20 ml reacted with HCl. 20 ml 0.17 molar. So you can know you can calculate what is the limiting mole. I think so. So after you know the limiting mole, so you know the okay, let's see. Yeah, that's the strategy. So initial mole of HCl. Why we want to calculate the initial mole of HCl? Because you want to know. So mole from the molarity is mole per liter. So 20 to 0.17 0.17 mole per liter times 20 ml divided by 1000. 20 divided by 1000 times 0.17. Okay, 3.4 in, okay, this is correct. So now you have to calculate the mole of K2CO3 and 250 ml, as I mentioned just now. You have to calculate what is the mole number and 250 ml. So the mole of 0.65 gram divided by molar mass. So you obtain the mole of K2CO2. Okay. So the mole in here, the mole in the sample will be similar with the mole in 450. The mole, okay, let's say, what is the mole now? 0. Let's say that's the mole, 3.4. So the mole, 3.4, negative 3 mole. So, and then you in, and then you delete it. So, should do molarity is a mole per liter. So this is why, because later on you want to decide what let's say let's try this is correct now. Molarity is mole per liter. So the mole is 4. Two hundred 250 kilograms divided by 1.18, 0.018 812 molarity. initial mole of oxygen and then mole of C2 mole into and then mole in 20. So let's say we calculate this one. Now this and this. So if you want to know more in 250, we are understand. So now we have to calculate what is a mole in 20 now. Because this one will be diluted. So diluted will make it this one. Okay, let's try. And one V1 and so this one. So one and 20 and 0, 1, 8, 2, volume 250. So and one so this is 0 0.23515. So mole is 0. Mole per liter times 20 ml in liter. 0.2. So times y okay. I think you try to settle this first. It's quite confusing. I think it's correct. Somewhere correct. So I don't know what's going on. So you calculate the mole of the mole number. Calculate the mole of equals CO3 into 140 L, and then you have to calculate the mole in the ml, because the mole number of here is not similar with the mole number of here. Okay, because it's already diluted. And then you can calculate the mole of HCl reactor. Okay, so you can calculate the mole of HCl reactor, because from the equation, 2HCl will react with 1 mole of HCl3. So you get the mole reactor. So see here, you have two types of mole HCl. This is axis, this is reactor. So this axis minus with reactor. So we can obtain the mole that will be undergo the second titration. So since 1 mole of now sodium hydroxide is related to 1 mole of hydrochloric acid, so the mole remaining similar to the mole of sodium hydroxide. So you know the mole of sodium hydroxide, so you can calculate the molarity, because you already know what is the volume. No, because you already know what is the molarity, you can calculate the volume. So molarity, you know, volume you have to calculate, and the mole number you already know, and then molarity is equivalent 0.12 molar, and then we can calculate the volume. So you can obtain 22.1 and alright. So please try this one. Try it slowly. I think you can get the answers. Alright. A few more slides. A sample of sodium hydrogen carbonate. Sodium hydrogen carbonate was tested for its purity using the following method. 0.4 gram of solid sample was dissolved in 100 ml of water and then titrated with 0.2 molar hydrochloric acid using metal orange indicator. The volume of acid required for complete neutralization is 2.375. So you can write the chemical equation balance for the equation reaction between sodium hydrogen carbonate plus with hydrochloric acid. So you can okay. And then titration curve, chemical equation done. Titration curve of the output reaction. So the titration curve, remember what is on the top is hydrochloric acid, strong acid. So here in the is sodium hydrogen carbonate. So it should be equivalent pH more than 7. No. It's less than 7 because it's a strong acid. So we add on what we added is HCl added. So at the beginning, uh, the it's a very basic question solution. It should be start from here like this. Okay, all right. Okay, so this one is HCl. Okay. So HCl, and then this is a strong acid. This one is base. So initially should be in a base. So this is why the pH is start on the top. Okay. So the equivalent point for this reaction, equivalent point is pH is then 7. Okay. So this is a 7. So equivalent point is then 7. So why we start from here? Because this is initially is the base, so pH should be higher. When we add more, volume of hydrochloric acid, so increasing the pH will be reduce toward acid. Okay, because we adding the acid. All right. Determine the purity of sodium. So asking about purity. So if purity, so sample 0.4 gram, so you have to calculate from the titration what is the real gram times. Okay, so this one is a direct titration. It's not a back titration, it's direct titration. So mole of acid, molarity, volume, you can calculate the mole of acid. And then from the equation, we know what is the relationship 1 to 1. So you can calculate the mole number of sodium hydrogen carbonate. This is the okay. This is the mole of sodium hydrogen carbonate, and then from the mole you can calculate the mass. Then you get the mass. After you get the mass, you can calculate the purity. Okay, so you can get the percentage purity. All right. Question 3. Write 3 properties of primary standard. Primary standard. We have a few options, properties of primary standard. So this is among the answer. It should be high purity between 100 to 105%. High stability, no water content, meaning that not hygroscopic, high equivalent, cheaper, easily available, chemical soluble, readily. So, example of primary standard, anything can be any chemical from the bottle or from chemical from the supplier. We give you sodium carbonate. You can name it any primary standard, what? HCl minimum. Okay. So this question is asking you about back titration. Back titration is required in some chemical analysis. For example, in distillation, give two reasons why back titration is employed. We can say the rate of reaction is slow. No indicator can suitable. The color change at the endpoints cannot be observed. The endpoint very far from the equivalent point. Standard solution. So you have a lot of option answer. All right. So I think that's all for this video for acid-base titration. The next video we will continue on the topic 4 on the complete section titration and then precipitation titration and also redox titration. Okay. All right. Thank you very much. See you again on the next